Hello. Good afternoon. Welcome to the 12th annual Dean W. Lytle Electrical and Computer Engineering Endowed Lecture Series. I'm Radha Puvendran. I'm chair of the Electrical and Computer Engineering Department of the University of Washington. I'm glad you can join us today. This is the EC department's premier annual event featuring internationally renowned researchers in the field of communication and signal processing. I'd like to start by thanking everyone involved in organizing this year's event, especially our faculty host, Professor Les Atlas, who had done tireless amount of work to make sure this event goes very well. And also the chair of the Lytle Lecture Series Committee, Professor Miriam Fasil. Professor Fasil also serves as the EC Associate Chair for Research and Education, and she is also the co-lead of the NSF Tripod Initiative, Algorithmic Foundations on Data Science. The Lytle Lecture Series honors the memory of Professor Dean W. Lytle, who began his career as an assistant professor in the department in 1958. He was a beloved teacher, mentor, and intellectual powerhouse in the department. Professor Lytle's research focus was in communication, networks, probability, and signal processing. He authored 2 textbooks, and his consulting work included appointments with Boeing, Honeywell, and Bell Telephone. The Lytle Endowed Lecture Series was made possible through a collective fundraising effort by the Lytle family and Professor Les Atlas, along with Louis Schaff. Together with the help of alumni, friends, and colleagues who were positively impacted by Professor Lytle during his 40-year career at University of Washington, they were able to raise the capital needed to make this lecture a permanent event and a premier one. This time, I also want to acknowledge Steve Perrin, who is here among the Lytle family. Others couldn't join today. Now, introduction to Professor Les Atlas, who has been instrumental in bringing the speaker today. I'd like to first point out when he started. He started as an assistant professor in the department in 1984 and continues to be the leader in signal processing research and education activity in the Pacific Northwest. His work has an impact on signal processing for dynamical systems, time frequency analysis, and non-stationary statistics, with application to streaming data, acoustics, machine learning, machine monitoring, sensor arrays, speech processing, and auditory sciences. His publication, Improving Generalization with Active Learning, was foundational to the machine learning areas of active learning and selective sampling. For his achievements, Professor Les Atlas has received prestigious Virginia Merrill Bolledel Scholar Award, a Fulbright Research Scholar Award to visit Germany, and a 2017 Amazon Catalyst Award. Among other things, Professor Atlas also was instrumental in connecting many of our junior faculty with Dr. John Tate from ONR in terms of supporting their career. So at this point, please join me in welcoming Professor Les Atlas, who would like to offer a few remarks about our invited Lytle speaker, Professor Stéphane Mallat.
Thank you, Radha. I'm really honored to be welcoming this year's Lytle lecture speaker, Stéphane Mallat. He's a data sciences chair at the Collège de France since 2017, distinguished research scientist for the Center for Computational Mathematics at the Simmons Foundation Flatiron Institute in New York. Dr. Mallat received his PhD from the University of Pennsylvania in 1988, after which he became professor at the Courant Institute of Mathematical Sciences. In 1995, he became professor of applied mathematics at École Polytechnique Paris and department chair in 2001 there. From 2012 to 2017, he served as professor in the computer science department of ENS in Paris. He is known for his fundamental work in wavelet theory with major impact in machine learning, signal processing, music synthesis, harmonic analysis, and image segmentation, among other areas. He's a member of the French Academy of Sciences, a foreign member of the US National Academy of Engineering, an IEEE Fellow, and a URSIPCO Fellow. In 1997, he received the Outstanding Achievement Award from the SPIE Society and was a plenary lecturer at the International Congress of Mathematicians in 1998. He also received the 2004 European IST Grand Prize, the 2004 INIST CNRS Prize for the most cited researcher in engineering computer science, and he's about to hit 100,000 citations in Google Scholar, highest I've ever seen. He's done 2007 EADS Grand Prize of the French Academy of Sciences, the 2013 Innovation Medal of the CNRS, and the 2015 Signal Processing Society Best Sustaining Paper Award. Today he's going to talk about mathematical mysteries of deep neural networks. Please join me in welcoming Stéphane Mallat.
Thank you, Frank. Thank you so much, Les, and thank you for this invitation, for these prestigious lectures. What I'm going to try to do today is not only introduce a deep convolutional network, which I suppose many of you know, but introduce it in the larger context of machine learning and also try to give ideas of what are mathematical questions which are currently behind these amazing algorithms. So machine learning and data science, basically it's about extracting knowledge from data. So what has been so new during the last 10 years, as you know, is the massive increase of data, the increase of computer speed, but also relatively new algorithm. I say relatively because deep neural networks were around for quite some time, but because of the mix with data and memory speed of computers, suddenly very different results have appeared. And right now we are in a situation where basically these results are not understood. They have been touching many areas of data science, speech recognition, automatic language translation analysis, image recognition, in particular face recognition. You all know that the world champion of Go has been beaten by a machine basically using deep neural networks. But also in our everyday life, we see it now appearing in autonomous cars to guide the cameras and, of course, medical application diagnostics. So beyond the applications, what is behind all these applications is the fact that you have huge data with many, many variables that you need to analyze. So these huge data may be recording of audio, which corresponds essentially to about 1 million points per minute, or images about the same order of magnitudes, about 1 million pixels, which corresponds to the different variables of your data. Text, about, again, 1 million letters within a book. And of course, you have much bigger data sets, such as social networks, where you'll see billions of agents which are interacting. And the science, really, of very high dimensionality until now was physics, where within few grams of matters, you have trillions and trillions and trillions of atoms. Now, the problems that we are facing when we look at this data is to try to answer questions about the data. So recognition of images are of that type, what is inside the image, or sounds, medical diagnostics, and so on. Statistical learning, which has been growing since about 10 years in a very fast speed, is behind what we now call the revolution of artificial intelligence. So if you think of artificial intelligence, I've been taking a course of artificial intelligence when I did my PhD, and at the time it was essentially about symbolic calculations, about trying to understand how to apply logic to logical statements in order to infer new statements. That was what was behind artificial intelligence in the 70s and 80s. What we've been seeing nowadays through statistical machine learning is a wave of empiricism. Now, it's interesting when you look a little bit at the topic from a little bit far away. As I said at the beginning, all this domain is about extracting knowledge from data. Now, this issue of understanding what is knowledge is, of course, at the core of philosophy, and this has been discussed for thousands of years. If you begin at the antiquities, you have on one hand a completely rationalist view of what is knowledge through Plato, where essentially knowledge is within us and you shouldn't use your senses or any type of data to access knowledge because that's going to trick yourself. And on the other end of the spectrum, you have approach like the one of Aristotle, where baby is seen as a body with absolutely no knowledge, like clay, which has to be formed through experience, through acquisition of data. Now, these oscillations on the view of knowledge has been going on across century when theory has developed to try to understand knowledge. So I'm French. I'm basically on the rationalist side of that screen. Descartes. For Descartes, mathematics is a science. Physics is not a science. Medicine is not a science. Physics and medicines are based on observations. You cannot trust observation. This is not about science. Only mathematics is about science. You go to the other extreme, and you have the Anglo-Saxon world. Locke. For Locke, there is no such thing as priors. The only thing you can do is get information from data. The only thing that is reliable is data. If you take Hume, Anglo-Saxon world again, causality doesn't exist. The only thing that exists are sequential events. You can say that something happens before something else, but there's no way you can prove that something produced something else. So on these alternations of view on knowledge, in the middle you have philosophers such as Kant, who raise a totally different question. Instead of asking what is fundamentally knowledge, he asks the question what it is to know. How can we try to understand the whole process of knowing, which in some sense is much closer to the type of questions we are raising today. Now, these alternation between rationalism and empiricism is exactly what has been happening in artificial intelligence. Nowadays, we are in a completely empirical phase. Still, there are key questions to understand how to go in between these two. If you think of machine learning, you have priors. This is the Plato view of the problem, and you have data, and the whole problem is to integrate the two. What is the nature of knowledge that we extract from data? How can we represent that mathematically? So you may think, at the end of the day, who cares? If you have a system that works, why is it so important to understand why? Maybe one reason is that personally, I wouldn't go right now on an airplane which is driven by a deep learning algorithm. Yes, the plane hasn't crashed until now, but no guarantee that it will not crash in 10 minutes. That's not quite a satisfying answer. If you want to have engineering systems which are robust, at one point you do need to understand. So, to understand, let me come back a little bit to the core principle of what is a learning algorithm. As I said, the key element is to try to answer a question that is going to be raised on a piece of data. So X here will be my data. Here it's an image, so the kind of question you may ask is, what is this animal? The answer is going to be Y, in that case, a dog. So what is so particular about learning algorithms? A learning algorithm is a standard algorithm. There's just one twist. There is a huge number of parameters which are embedded within these algorithms, which are not fixed in advance. And to fix these parameters, you have a learning phase where you are going to try to optimize the parameters so that the algorithms takes training examples where you have specified the data xi and you have specified the true answer. And the algorithm is going to try to produce an answer which is as close as possible as the one that you have given to the algorithm. So basically, it's a very stupid phase where the only thing that you are asking to your algorithm is to reproduce the example that you gave him. On the way, it is going to set up the internal parameter of the algorithm. So that has no real application by itself, unless the algorithm is able to generalize. Generalize means that now, if you give to the algorithm a new piece of data X that it has never seen, it will indeed be able to come out with an answer which is very close to the true answer. So when you are studying that field, you basically have two types of approach possible. One is mathematical. The mathematical approach will try to understand what is the source of generalization. Why is it possible indeed to generalize given a training set? The computer science side will rather try to develop the algorithm which actually is able to generalize and get very precise answers. Now, right now, we are in a phase where mathematics is very far behind. They are remarkably efficient algorithms, but we don't understand mathematically why they work so well. And that's the kind of questions that I'll try to ask today. So let me come back to this miracle of generalization. This miracle is, in fact, very simple to understand. It's based on the fact that you do have an a priori on the problem, and this a priori tells you the kind of regularity you have in the phenomena. Now, to make that more precise, I'm going to take a very simple example. Suppose that you have a bowl of water, and in this water, you have two parameters that you can measure, which is the temperature of the water and the pressure. And the water can have three states. It may either be ice, solid, or liquid, or gas. And your problem is to find whether the water is gas, solid, or liquid. So you basically have two variables. X has two variables, pressure and temperature. You make an experiment. The temperature is in between 0 and, let's say, 100 degrees, so it's very likely to be liquid. And then you make new experiments to have a training set. And all these points correspond to temperature and pressure where the water is liquid. Here, the temperature goes below 0 degree, it's solid, and high temperature gas. So now the problem is you are given a new point, which means a new measurement of temperature and pressure, and you ask, is it liquid, solid, gas? This is about basically finding the frontiers between these three zones. So you can try. This could be a frontier. And if that's the right frontier, you will say that X is in fact gas. Now, when you look at that, you'll feel not very comfortable with this frontier because, after all, physics is regular. There is no reason why suddenly the frontier should have these jumps. A much more natural frontier would be this one. This is just, in some sense, the most regular frontier you can have by putting a frontier between the liquid, solid, and gas and being far away from the examples. So as you see, if you make that hypothesis, you have a chance to have the true frontier if indeed the true frontier is regular. So that's the key point. What kind of regularity your problem has, and how can I fill up the non-known domain given the experiments by using this prior on the regularity of the problem. Okay, so that's the mathematical view of the problem. The algorithmic view of the problem will be to try to find actually a way to know whether that's gas, solid, or liquid. And the easiest algorithm you can think of is the nearest neighbor algorithm. What is it going to try to do? It will find the closest point to x, and because the closest point is liquid, you'll say it's liquid. This is essentially about finding a frontier which is piecewise linear between the different domains, which is uniformly spaced between the different examples. Okay, so as you see, the problem doesn't look so difficult. So why did we need so much time to reach the stage where there are actually algorithms that do work quite well? Because in fact, the problem is very, very, very difficult. And the reason why the problem is so difficult is that you don't have two variables, like in the example that I gave you, but you typically have several million variables. Let me come back to an image. As I said, an image is about 1,000 by 1,000 pixels, so about 1 million variables. Each variable takes its value in between 0, black point, 1, white point, okay? So an X is a set of 1 million variables. It's an image. Now, you ask a question, what is this animal, dog, cat? So for that, you'll take examples. Here you have 3 examples, 3 cats. Each cat is an image which corresponds to 1 point in my space, exactly like I did for the water, but a point now, again, has 1 million variables. I couldn't draw a space of dimension 1 million, so I just draw 3 dimensions, but imagine it. Now you take examples of dogs, and now you have 3 points. Now, you could try to do the same thing. What's the closest neighbor? The problem is that all the examples you are going to have are very far from your X. You see, none of these images looks exactly like this image. You could try to compute how many images you would need in your database in order to make sure that one of them is close to this one. Well, imagine that you would like that the distance is smaller than 1/10. That means that each time you move by 1/10 along any of the pixel, any of the axes, you have 1 example. So how many examples do you need? You would need 10 multiplied by 10 by 10, as many times as the number of axes, 10 to the power d. So I gave this example this morning. If d is larger than 100, 10 to the power 100 is more than the number of atoms in the universe. It's huge. And d is not going to be 100, but in this case, it will be 1 million. So there is no way you can have so many examples, which means that your examples are completely isolated in this huge space, and still you will need to interpolate between. So that means that in order to generalize in very high dimension, you need to have a very strong regularity which allows you to infer the property of all the points, all the examples, despite the fact that you have very few in your database. So how does learning approach that problem? As I said, initially, you have, let's say, 2 classes, dogs and cats, and the points are very isolated. It's a mess. The dream of machine learning is to try to find a miracle change of variable. That means that from X you go to a new set of variable that you can think as features of X, characteristic element of your data. And in this feature space, what you hope is that by miracle, your 2 population is separated. Separated means what? It means that you can find a simple plane which is going to separate the dogs and the cats after you've done your representation in terms of these features. What does that mean? It means that if you move perpendicular to the plane, you are going to go from the dogs to the cats, so you have a kind of discriminative directions which allows you to move from one animal to the other. Let me give you another example, not dogs and cats, but fire trucks. Imagine that the problem is to find out whether the image includes a fire truck or no fire truck. The image can be very complex. A very naive and simple way to do it is to count the number of red points. If you have a big red fire truck, you should have many red points, and you count the number. If it's big, it should be a fire truck. Otherwise, it's a normal car. You are going to commit an error, but that would be the discriminative direction. Now, the problem is that very often, it's going to be much more complicated to find these features which carry some information. Let me still suppose that they are God-given, you know them from prior information about the problem. Let me just, for now, address the problem of how to put the frontier. This plane is characterized by the orthogonal direction to the plane. The orthogonal direction has some coordinates over there. So how do you find whether you are on the left or the right side of the plane? What you do is basically a projection on this line, which is, in mathematical terms, an inner product. Another way to view it, it's a vote. You are voting so that each feature gives you a vision whether it's rather on the left or the right. The weight of the vote is the coordinate of the orthogonal direction to the plane. And if the vote is larger than a certain threshold b, then you know that you are on the left. If it's smaller, you know that you are on the right. So the idea is basically build a feature vector which gives you weak information about the problem, and then organize a vote of your weak features in order to have a strong feature on the problem. Now, that part is not so difficult. What is really difficult is to find these features. There are problems, again, where I said you have prior information. But there are problems like dogs and cats, which are really complicated. And if you don't have enough information, the idea is to learn the features themselves. And that's the point of view of neural network. So what is a neural network doing? A neuron, and that comes from models from biology in the 50s to model cells from frogs. French, that's probably why I'm so attracted to that. So you have the input, V1, Vm, which are multiplied by the weights of your neuron. That corresponds to the dendrite. You sum up the sum of the multiplications. And if the sum of the multiplication is above the threshold, which is defined by a nonlinear rectifier, then you output the weighted sum minus the threshold. If it's below, you output 0. So what a neuron is basically doing is setting a hyperplane which is separating the domain in two regions. The way we are going to write a neuron is, or symbolize a neuron is that way. You have the different inputs. That's the body of the neuron. That's the output, which in biology is called an axon. Now, a neuron by itself is a very simple computational unit. Where things are getting much more complicated is if you take your neurons and you organize them in a network. So that's an example of network. You have here the input, your X, 1 million pixels, for example, for the image, which are input into many neurons. Each neuron is going to do its own computations with their own weights. It's going to output a result, and that will be the first layer of your neural network. And then this first layer is fed into a whole series of neurons again, which are going to output a second layer, and you can cascade like that as many layers as you want. The last layer will be your final features, these feature vector phi of x, and then you are just going to recombine them linearly to output what you consider as being the estimation of the answer to the question. Okay, so if you put such a neural network, you have plenty of parameters. What are the parameters? The parameters are the weights of each of the neurons. And in a typical neural network, you can have several millions or hundreds of millions of such parameters. Now, how are you going to learn these parameters? exactly the way I described previously. You are going to have a database of examples, which are your data and the known answer to the data. And what you try to do is to optimize the weight so that the output of your network has a very small error relatively to the true output. In other words, you are going to minimize an error which depends upon this big matrix of weights. How can you minimize this error with a gradient descent algorithm? We'll come back to that. So there's two kinds of questions on such neural network problems. One is how to learn the weights. The second one is how to fix the architecture in order to answer and get a precise view on the problem. The architecture is about prior information. Learning the weight is about learning from the data. Okay, let me first go on the learning of the weight. So why is the problem so difficult? You basically have to minimize an error, which is a function of many variables. Now, if you look at the profile of the error as a function of your variable, the reason why the problem is very difficult is that this is what is called a non-convex problem. The typical algorithms that we use, gradient descent, is a very simple algorithm. The idea is you have a ball, and you just let your ball roll down on your profile. So the ball is going to go in that direction because it goes down. That's the direction of the gradient. And the only problem is that once it will reach that point, it's a local minima, it will be stuck. So you are not going to reach the global minima, which is here, but just this one. So under what conditions that solution is going to be a good solution? The condition is basically that all the local minima are low enough. Is there any way to guarantee that? That's the mathematical problem behind the optimization. Currently, there is no good theory which can guarantee that indeed these gradient descent algorithm will work. In fact, anybody who makes experiments on these deep networks knows that often it doesn't work, but often it works. Why? There are some ideas, but it remains a very open problem. So let me move to the second kind of question. The second kind of questions are about the architecture. How should you organize the architecture of these networks in order to get a precise result? Now, I'm going to give an example on image. So this is the input X, and that will be the neurons of the first layer. Now, you have one particular class of neural networks, which are called convolutional networks that were introduced by Yann Lequin. And the idea is very simple. If you want to do a recognition of an object, let's say my hand, if the hand moves, it's still a hand. So normally, the recognition shouldn't depend upon the position of the hand. So if you have a neuron which looks at that size, that domain of the image, or that domain of the image, because the hand may be here or here, there is no reason to use different weights. So what a convolution is going to impose is that the weights are the same everywhere, and you have the notion of invariance. The weights are invariant to positions. Given these constraints, you are going to get the output of the first layer, which is, in this case, going to be a series of images. Now, then you continue. You define the second layer of weights corresponding to neurons, which are going to process the output of the first layer in order to get an output on the second layer, which is, again, invariant to translation because the object doesn't change nature when it's translated. And you iterate until having the last layer that you recombine to get the final answer. So the core element here in the architecture is this invariance to translation. The surprising fact that came out of these deep convolutional neural network is that they obtain remarkable results, not just on one application like image processing, but on many different types of data. on images, on speech, on language, on biodata, medical data. And the kind of question that comes out is why these architectures are able to solve these so different problems. What is in common between these different problems? And that's where you touch the mathematical question. What is the regularity of all these problems? Is the nature of this regularity similar when you go from medicine to physics to literature or to image analysis? So that's an example which is well known, coming from a database called ImageNet, because in 2012 you had this paper from Hinton and his collaborators showing that suddenly you could get much better results on these very complex images compared to standard algorithms. And there you have to recognize that you have a Dalmatian and cherries, mushrooms, cars, and so on. You see the kind of complexity. Now, if you look at the error rate of the algorithms, the standard most advanced algorithms on that kind of database was reaching an error of 26% in the years 2011. There has been a jump when the deep networks were powerful enough to attack that kind of database. And since then, the error has been dropping down to 3%. Now, this is in red because this is human performance. On such a database, humans do typically an error of the order of 5%, and the network can go below. Now, it doesn't mean that human vision is not as good as deep network. In fact, human vision is much, much better than deep network, has an ability to deal with much more diverse type of data. But when you have a very specialized task, and not everybody knows what is a Madagascar cat, then a deep network can be better, and that's the case for face recognition. Now, you have very different type of application. Let me just show you applications to audio recognition. There is a problem that has been considered as very difficult until about 2 years ago, source separation. So you have two different speakers which are speaking at the same time, and you are going to hear the type of sounds it gives.
The most significant scientific publications were studies of birds and animals. Up and down.
Very hard to understand. That's typically the kind of thing that you have when someone is speaking. That's called also the cocktail party, and you have all kinds of voices around. So the problem is, can you take this mixture of two signals and separate them? I'm going to make you hear the results of a separation done by a deep network.
This allows the shaft to change its length and direction as the car wheels move up and down.
That's voice one. Now voice two.
His most significant scientific publications were studies of birds and animals.
It looks almost perfect. This is the kind of result that in the signal community we believe was impossible to reach. These two speakers were not in the database. In other words, the system has been learning from different speakers than the one that you are hearing. What's happening? How come a deep network is able, with a similar architecture than the one I showed for images, to reach such high precision? Now, why is understanding important? One reason is that these deep networks can fail in a very brutal way. These are images which were, from ImageNet, perfectly classified. Then, to these images, you have a very small error that was introduced, that's called adversarial noise, introduced in a way to try to make the network fail. These are the resulting images. To your eyes, they look the same. It's as easy to recognize. For the network, they are all ostriches. What does that mean? That means that your network is very unstable. Instability means very hard to control. As long as you don't understand the math, you won't be able to control that kind of thing. And as I said, personally, I wouldn't go in an airplane where that kind of thing happens. So, mathematics. Why is it important? So the kind of question that we're going now to ask is, why does it work so well? And in what sense it's related to some type of regularity. So obviously, I'm not going to go into any detail, but I'd like just to show you the type of mathematics, or what does it mean to do mathematics in such a field. There are basic intuitive notions that you have behind that. First of all, when you have a scene like that, there are structures of different size. You have large structures like the overall building, intermediate structures like the lamps, finer structures like your own faces, which themselves have the eyes and so on. So a very classical approach to a problem like that is to separate the structure from sizes, scales. That's exactly what deep networks do. How? The neurons first aggregate the information on very small neighborhood through these convolution filters. And then you have a subsampling, then the next neuron aggregate the information over a larger domain, and larger domain, and larger domain. So you see this kind of hierarchical information across scale going across the different depths. Second thing, I said we have some prior information. Translation doesn't change the notion of an object. That's called symmetries. I'll come back to it. And last thing, there is this notion of patterns. I said a face has eyes. The eyes has structures. Somewhere the network should be able to use this notion of structures. How can you express that mathematically? So the idea of trying to go along the roads is to simplify the network and therefore being able to interpret the result of the network. Why is that so important? If you use the network, for example, for medical or for legal reason, you would like to understand why it reached that decision, especially in a legal framework where you may re-question the results of a network or an advice of a network. So I'm just going to quickly give an idea of why it makes sense that these criteria comes in. The first concept is this idea of separating scales. If you take a problem where you have many interacting variables, let's say particles or agents in a social network, they all speak to each other. But the very strong interactions are the one corresponding to the close particles. Let's say yourself with your family, or a particle with the nearest one. The more far away particles, you don't need to look at the individual influence on this one. You can look at the influence as a group. The even more far away particle, you can regroup them even more, and look at the influence as a group on the final one. What's the result of that? Instead of having D interaction, you have log D interaction, much fewer. And that's going to break your curse of dimensionality. Of course, the problem will be you need to understand how these groups all interact. How do you do that? To do that separation across scale is the notion of wavelets. And that connects us to signal processing. So in the 80s, people began to try to understand how to represent an image in order to compress it with as few bits as possible. That was very important for transmission storage with small hard disk. If you take an image, what wavelets are going to do is essentially extract edges at fine scale. So wherever there is no edge, the wavelet coefficients will be 0. Whenever you are close to an edge, you are doing a kind of edge detection. You measure the transition of the image within different directions. You will see the edges of the image in different directions. And you do that at different scale with what is called a filter bank in signal processing. And that was a major topic in the 90s, early 2000s. OK, that looks a little bit like a deep network. You have this cascade, but no nonlinearities. OK, question is, how do you take that and build something which is useful for classification? The second ingredient you need is this notion of symmetry. OK, so what is this idea of symmetry? The idea of symmetry is the following. If you have a data x, and you transform your data with some transformation t, t is going to be considered as a symmetry if the answer of the question is the same for x and for x transformed. You will say that it's an invariant. So let me give you an example. Take a square. If you rotate the square by 90 degrees or 270 degrees, it's still a square. So the squares have symmetries. If you take a circle, any rotations makes it a symmetry. Now, in, when was that? 1911 to 1932, that 1911 is the birth of Galois. So who is Galois? Galois is a French mathematician who has a very romantic story. So that's a story that mathematician likes to tell. He died at age 22 in a duel for a woman with whom he was in love. And the night before he died, he wrote his testimony, his mathematical testimony. And the mathematical testimony of Galois was the group theory, which is behind all what I'm describing. And he died at 22 in the morning during this duel. So why, how come is that related? Galois obviously was not interested by deep network. Galois was interested by the resolution of fifth-degree equation. And the question was, can you compute analytically with radical the solution of a fifth-degree equation in the same way that you can do for the second-degree equation? The amazing idea of Galois was not to try to compute it, but to suppose that if x is a solution, what kind of transformation I can apply to x so that x remains a solution. In other words, the idea of Galois was to study this equation by looking at the symmetries of the equation. This is exactly the same ideas. In order to understand y of x, the answer to the problem, we are going to look at the transformation which doesn't change the answer, the symmetry. And since then, this has been all across mathematics as one of the key tools to understand mathematical structures. Now, symmetries define the notion of groups. If you cascade two symmetries, you have a symmetry. And one of the ways to capture prior information about a problem is to know what kind of symmetries you have. Translation, you rotate an object, it's still the same objects, and so on. If you want to capture that, one way to do is to make sure that your representation has the same symmetry. That's one of the key domains of mathematics. So in the case of images, typical symmetries are, as I said, translations, or you can deform image. This is an example on paintings. Small deformations correspond to the same paintings. Big deformations are not symmetries of painting recognition. It defines a new painting. So understanding this symmetry, capturing them, is a key element. Now, if you try to do mathematics on a problem like that, the first thing you try to do is not get a state-of-the-art result, but rather try to define the simplest problem which can reproduce the kind of property of what you are looking for and which you can understand mathematically. So one way to do it is to say, okay, can I completely avoid learning the weights and fix in advance the weights? And you know, by the way, I know how to compress images with wavelets. Why not trying wavelets? And you put wavelets in all the filters, exactly like the filter bank. This is not crazy. Why? Because you can prove that with wavelets, you are going to have something which is invariant to all the deformations that you need to be invariant to and to translation. So you can try, and that was what has been done. In that kind of framework, the only learning will be in the last layer, here. So, does that work? You can apply that to image recognition, but just to show you that there is not just images in life, I'd like to show you the example in the case of physics and body interactions. So in the case of physics, the problem is essentially to learn physics. So how can you characterize physics? One way is to define the physical laws. For example, the Newton equations, If you have a gas, Boltzmann equation, electromagnetic Maxwell equations, and so on. And then you have your equations, and if you want to understand the evolution of the system, you compute the solution of the equation. But that can be incredibly complicated when you have many particles interacting. Now, one other way to do it is to say, I don't know physics, I don't know the equations, I'm just going to learn it from the data. So you have example of physical system where you can observe the state of the system, and you can measure, for example, the energy, and then you can try on a new set of data to infer by doing a regression, learning, what will be the state of the system. Let me give you an example from quantum chemistry. So quantum chemistry, the problem is the following. You have a molecule, and that's extremely important in industry, for example, pharmaceutical industry or industries developing new materials. And you'd like to know whether your molecule is stable. So you'd like to compute the energy of the molecule. What do you know? You want to build a new material, so you are going to define the position of the atoms and the number of charges of the atoms. And now the problem is to compute the energy. So you can compute the Schrödinger equation with n-body. If you have 24 hours of computation and a huge computer, you may be able to do it for a large molecule. Or you may say, I don't know anything about quantum chemistry. Let me just use a database and do a regression from the database. OK. But you cannot just do things from data. You need prior information. What is your prior information? Even if you are not a physicist, you can imagine. If you take a molecule, you translate it, the energy is not going to change. If you take a molecule, you rotate it, energy is not going to change either. If you slightly deform it, the molecule will have an energy which will slightly change. You have a problem which is not very different, in fact, from image processing. So from that point of view of symmetries, quantum chemistry and image processing are not so far away. So maybe you can use the same kind of network to solve it. And in that case, why not using a network where you don't learn anything because you know the symmetries? So you can mathematically specify the weights. And in that kind, it was wavelets that we've been putting here. What you see here are the internal weights. In fact, the internal weights looks a little bit like orbitals of molecules, from which you compute your invariance. And the only thing you learn is the final classifier. So does it work well? Yes, it works well for organic molecules that have been tried on the kind of database that has been tried, as well as deep network. But all these experiments until now have been done on database of small molecules. And when things are small, it is much simpler. And I'm going to show you the equivalent on image processing. If you use the same kind of architecture without learning on digits, you can get great results as well learning or without learning the weight. So it looks like learning is useless. But if you then, sorry, that's a second example, recognizing texture. These are simple examples. If you go to problems where your images are really complex, with all kind of structure, dogs, cars, and so on, deep networks do much better than any network where you will have specified the weights. So we are back to the question. Prior information in that case is not enough. What is learned by the network? And these are the kind of core questions that are very open from a mathematical standpoint. So let me just give you a hint of a possible answer. In this domain, what is really important are features. A face is structured of features. So you'd like to specify the features. And one way to do it is to put these features in a big bag, which is called a dictionary. It's a big matrix whose columns corresponds to the different features that you are looking for. And decomposing your information as a sum of features is like finding a sparse code, exactly like in data compression, where your information is going to be decomposed as a sum of few structures, which are the features from the dictionaries. Now, you can do that with a sparse code, where you put in input your representation, and the output, you have the sparse code calculated with a deep network. So we did few experiments with that, and I'm going to conclude on that kind of thing. If you don't learn anything on a problem as complicated as ImageNet, you just use your prior information, symmetries, invariant, you make a very big error, 60% of error. If you just learn, you don't use any prior information, you just learn a dictionary of patterns. You apply it to your data, you still make a very big error, about 50%. If you mix the two, if you first incorporate your prior information, the fact that you know that there are invariants, you eliminate the source of variability, and then you learn the patterns through these dictionaries, the errors drops to the type of errors that are obtained by deep networks. There, you're obtaining an interpretable network. Why is it interpretable? Because the first phase corresponds to symmetries that you know. The second phase is about learning patterns, and you can go back in your network and look at the type of patterns that you're obtaining. And obviously, this is a long path to arrive to the ultimate performance that deep network have. Right now, deep network don't have a precision of 18 or 20%, but 3.8%. But as I said, mathematics is very far away still from true performance in these domains. So 5 years late, that's about the performance obtained in 2012. That's typically the type of delay that we are currently having in the mathematics community. So let me finish with this notion of interpretability and reliability. Why do we need to understand the black box? Right now, these networks are essentially black box. We put data, we have results, we optimize them. There are several reasons why. The first one, as I said, is getting explanations when these networks are applied in a social context. There are examples, in particular in the US, where these kind of networks have been used by courts, committees to decide whether a prisoner will be or will not be able to get out of jail. So obviously, the decision is not based on the network. The network just gives an indicator based on the behavior and the past of the prisoner, and the committee decides. However, whenever you have a machine which gives you an indicator like that, it's pretty hard for the committee to go against the recommendation of the machine because their responsibility is very strongly engaged. So what has been observed is that the impact of that kind of indicator is very strong. Now, you had the case where a prisoner came back and said, look, I don't understand why I was denied parole. What's the reason? So the committee came back to the company which had delivered the system, and the company said, we don't know, because nobody knows why. That's not acceptable, because legally, you need to be able to have the right to know the base of the decision. Second reason why it's so important is the existence of bias. We all know that this kind of system has a bias if the data has a bias. There is a well-known case that was in the past for a company which is Amazon, where such a network has been tried for hiring based on past hiring. And what had been observed is whenever you had a CV where the word woman was appearing, the CV was immediately going down in the pile, even if you were a man who has been a coach of women football team. It was going down. The reason is clear. In the past, in Amazon, there was much more men that had been hired, and because the regression was done on the past, these biases were reproduced. You can't control that kind of bias without understanding how the system works. Now, the reason why the problem is very difficult is that the notion of explanation is difficult. You have some problems where the explanation can be 1, 2, or 3 reasons. But if I ask you whether there will be a tornado over, let's say, Australia in 3 weeks, whether they will or will not, it's not based on 1, 2, or 3 reasons, but billions of variables corresponding to interactions of particles of very unstable chaotic systems. So explanations by themselves don't always exist, and in some sense you can view this system as being unconscious intelligence, in the same way that very often you don't really know why you are doing this and this. In the same way, right now, we have very little grasp. But in our case, we have a conscious system which controls the loop, and basically that's what people now are trying to do in that field. You need in some way to open the box, understand how it behaves. In other words, build a system which analyzes the box, which is not so far from a conscious system looking at the network. So one way is to analyze the inside. The other way, if we don't understand really how the box works in the inside, is to test the box. In other words, put certificates. And personally, I think that will be a very important stage for the development of that kind of technology. The fact that these algorithms are certified, because as long as there is no certification, there is no way you can guarantee the existence of bias, no way you can guarantee robustness, and so on. But these are very difficult problems, and they all require mathematics. So, in conclusion, what I'd like to say is that, yes, deep networks have very spectacular applications, and we saw them in many, many different fields, and there is something generic behind that. The problem to understand them are truly outstanding. It's very unlikely that we will get a final answer in the next 1 or 2 years, and you can see it by the fact that understanding a deep network in some situation is equivalent to understand the physical nature of a problem such as turbulence. Now, if you think of turbulence since the 1940s, all the best physicists have been trying to work on specifying property of turbulent fluids since the work of Kolmogorov. This is still an open problem. So we shouldn't expect that the solution will come like that. These are very complex, high-dimensional problems. As I said at the beginning, we are currently in a very empirical phase. And that's not so bad. The reason why the domain has been developing so fast was precisely that it got free from mathematics. You know, mathematicians have a tendency to be very conservative. There are things which are obviously right and things that you should not do because you are going to lose your time. And in that case, it did work, and surprisingly well. So doing completely empirical work is a very natural way for science to advance. That's the way chemistry, physics, and most biological science move on. But at one point, we need to come back to some rationalist approach to that field. And as you may see around you, about 90% of the research in this domain is essentially computational and empirical. So I can only encourage the students who are here to take a slightly more mathematical path, because there is not so much people doing it and a lot of things to do in that field. Thanks very much.
We have time for 1 or 2 questions. Any questions?
Can you go to the microphone just behind you? Yep.
So my question is, if our goal is to achieve these robust understandings of these problems, is there a way to know how much of our understanding can be rational, or sorry, how much of our understanding should be rational and how much can be learned from data?
Understanding is almost as synonymous, from my point of view, of a rational approach. But understanding doesn't mean that you specify all the parameters of the system. It means that you understand the nature of what is being learned. Let me give you an example. For example, understanding that what you've been learning is a group having that kind of properties. So that's what I mean by a rational approach. It doesn't mean, again, that you are not going to use data for finding the optimal solution.
More question? Yeah. You go to the mic.
So you talked about incorporating known symmetries as priors and then learning an ordinary hyperplane on top of that. But obviously the objects that we're learning about have many, many symmetries besides the obvious translation, rotation, etc. So how about learning the symmetries from data?
Yes.
Like, again, if you go back to Galois, if you know all the symmetries of the object, you know the object.
It's exactly what we thought. So initially what we began to do is use the prior symmetries that were known. And the obvious next step was, okay, let's now learn the symmetries. And we spent about 5 years trying to learn symmetries, and we failed. Now, one explanation is that we were just not good enough, and that's a very plausible explanation. But there is something else. Learning a group is a very complicated structure, because it's not just about learning the elements of the group. You have to learn the structure, the order. And these are very complex NP-complete problems. So yes, you can always fully specify a function from its symmetry group, but it's not clear that it's easy to learn. On the other hand, the day we finally said, okay, let's look at what engineers are doing in that field. How did they call the domain? Pattern recognition. Maybe they were not so wrong, and maybe it's about patterns. And the day we tried that, boom, we got 30% increase because suddenly we could learn the patterns. Why can we learn patterns? Because they are unstructured. So it's much easier to learn. So I have a tendency now to think that the symmetries are the elements which essentially belongs to our priors. And that's what allows you to move from very high dimension to, let's say, intermediate dimensions. You reduce a lot of the size of your space. Once you arrive in this intermediate dimension, then learning would be about patterns more. And then the learning is not so difficult, and you can go all the way. It may be wrong. It may be that we can learn symmetries, but that's what we thought, and we didn't do it.
Let's thank our speaker.
Thank you all for joining our 12th Dean W. Lytle lecture series. At this time, I would really like to thank Professor Stéphane Mallat again for joining us and spending time with us and sharing his vision and also experience. Thank you very much, and also inspiring our students. I also would like to thank Professor Miriam Fazel and Professor Les Atlas for their extensive work in securing Professor Mallat's visit here and allowing this wonderful evening to take place. I would be missing a big opportunity if I don't thank our advancement team and also events team, along with our audio and visual team, which has been fabulous for the last 5 years. So thank you very much for making these events taking place wonderfully. Finally, Steve, you're alone here today, but thank you very much to Lytle family for making this event happen, and also have the endowment in place for years to come, so that we can have incredibly well accomplished researchers like Professor Mallat in communication and signal processing visit us and engage with us. And finally, Dr. John Teague, not missing any of them from Washington, D.C., coming and attending. Thank you very much for doing that. I appreciate your support. Thank you all, and please join us in 269. There are some food, networking, and some evening to mix and get to know each other. Thank you very much.